Welcome back, everyone. United Kingdom's effort to design and deploy compact modular nuclear reactors is often referred to as SMRs, small modular reactors. These systems are being led by Rolls Royce and a number of government partners. The focus is on how they function, what makes them different from conventional reactors, and what their realistic potential is in the coming years. Please subscribe now. A small modular reactor is essentially a scaled-down pressurized water reactor built in factory conditions and transported to a site where it can be assembled more quickly than a conventional large-scale plant. Rolls Royce SMR Ltd, a consortium including Rolls Royce Group, BNF Resources and Exelon Generation, is pursuing this design. Their plan involves manufacturing major reactor components in modules within controlled environments. The modules are then shipped to the installation site where they are joined together. This approach reduces on-site construction complexity, lowers cost overruns, and shortens project timelines. The core of the Rolls Royce SMR design is based on well-established pressurized water reactor technology. In this system, uranium dioxide fuel is arranged in rods within the reactor core. Neutrons strike the uranium atoms, causing fission that releases heat. This heat is transferred to pressurized water circulating through the core. Because the water is under high pressure, it does not boil even at temperatures exceeding 300 degrees Celsius. The heated water is then passed through a steam generator where it transfers energy to a secondary water circuit. In the secondary loop, water turns into steam which drives a turbine connected to an electrical generator. Compared to existing gigawatt-scale reactors, the Rolls-Royce SMR produces about 470 megawatts of electricity. This is roughly 1/7 the capacity of the UK's largest nuclear stations, such as Sizewell B. The smaller capacity is deliberate because it allows the reactor to be constructed more quickly and in more locations. A 470 megawatt plant can supply power for approximately 1 million homes. By using a modular construction process, Rolls-Royce claims that a single unit can be built in about 4 years, once regulatory approval is complete. A crucial aspect of modular reactors is the containment structure. Rolls-Royce has designed its SMR with a compact steel pressure vessel that can be produced in factories and transported by road. This differs from large reactors where concrete containment structures must be cast on site. The smaller size allows for more consistent quality control. In addition, the design includes passive safety features. For example, in the event of a shutdown, gravity-driven cooling systems ensure water continues to circulate around the core without pumps or external power. Researchers at MIT and the University of Manchester have published studies confirming that passive safety designs can significantly reduce meltdown risks. Rolls-Royce emphasizes the use of existing nuclear fuel supply chains. The SMR is designed to use low-enriched uranium, typically enriched to less than 5% uranium-235. This is the same level used in most light water reactors worldwide. By relying on established fuel standards, the company avoids the need for specialized enrichment facilities. According to a 2023 report from the UK Nuclear Decommissioning Authority, compatibility with current fuel infrastructure reduces both cost and regulatory hurdles. It also ensures that spent fuel management can follow proven procedures already in place at existing nuclear stations. Cooling is another major challenge for nuclear plants. Large reactors often require direct access to the sea or a river for heat rejection. The Rolls-Royce SMR, by contrast, is designed with air-cooled condensers as an option. This means that the plant could be built inland without depending on coastal sites. Air cooling is less efficient, but it broadens the number of potential locations. A Science Advances paper in 2022 analyzed similar air-cooled designs and found that they maintain reliable output even under heatwave conditions, though efficiency losses can be 5 to 8%. Rolls-Royce engineers are working to minimize these losses with improved condenser surface area. Construction economics are really central to the UK SMR programme. Traditional nuclear projects in Britain, like Hinkley Point C, have suffered from cost overruns and decade-long schedules. Rolls-Royce argues that factory-built modules can cut costs to about £2 billion per unit, compared to £20 billion for a large gigawatt reactor. The UK government has committed over £200 million in funding, with additional private investment exceeding £500 million. The European Commission has also noted in policy papers that modular reactors could reduce the financial risks that have slowed new nuclear construction. One of the key advantages of the Rolls Royce SMR is scalability. Multiple units can be installed on the same site to form a power park. For example, 4 SMRs on one site would equal the output of a single large reactor, but with the flexibility of staggered construction. This modular approach allows utilities to match capacity growth with demand. In practice, a region could start with 1 unit and add more over time. Exelon Generation, a major US utility participating in the consortium, has highlighted this incremental growth model as a way to spread capital expenditure and shorten payback periods. Safety oversight is an important element. The UK Office for Nuclear Regulation began a generic design assessment for the Rolls Royce SMR in 2022. This multi-year process reviews design safety, security, and environmental protection. The assessment is expected to conclude around 2026, after which site-specific licensing can begin. During this process, independent experts from universities such as Imperial College London and the University of Sheffield provide technical evaluation. Transparency is key, because public acceptance of nuclear projects depends heavily on safety confidence. International interest has been growing. In 2023, the Czech Republic and Poland entered discussions with Rolls-Royce about the possible deployment of small modular reactors, and Canada, through Atomic Energy of Canada Limited, has also shown interest in collaboration. A report in IEE Spectrum noted that smaller nations, especially those without experience in large nuclear stations, see SMRs as a kind of entry point to nuclear power. The main appeal here is the combination of lower upfront costs and standardized designs, which help reduce the need for specialized national supply chains. Comparing the Rolls Royce SMR to older nuclear designs highlights its unique qualities. For instance, conventional reactors like France's pressurized water fleet require massive on-site civil works with reactor buildings that are over 50 meters high. By contrast, the Rolls Royce SMR fits within a structure about the size of 2 football fields. Older reactors often depend on active safety systems, which require pumps and diesel generators. The SMR's passive systems, however, reduce dependency on human intervention during emergencies. Furthermore, modular construction shifts much of the quality assurance to factory conditions, unlike older projects where variability in on-site labor led to costly delays. The role of small modular reactors in the UK's energy mix is quite significant. While renewables such as wind and solar are expanding, their intermittent nature means we still need stable baseload generation. Right now, natural gas fills this role, but it does come with emission concerns. Nuclear plants, on the other hand, provide emissions-free baseload power. A fleet of SMRs could complement offshore wind and help reduce reliance on imported gas. The UK Department for Energy Security has identified SMRs as a central pillar of its future energy strategy. Challenges remain. The first is financing. Even at reduced costs, £2 billion per unit requires substantial capital. Attracting investors depends on demonstrating predictable timelines. A second challenge is regulatory approval. Nuclear projects face rigorous review, and any design changes can restart the process. A third challenge involves supply chain readiness. Rolls-Royce is working with British firms such as System and Atkins to develop the manufacturing base, but scaling to multiple units will test industrial capacity. Finally, public perception remains a factor. Past nuclear accidents have left skepticism that can only be addressed through transparent communication and demonstrated safety. Research groups are examining technical details of SMRs that could further enhance performance. The University of Bristol has been studying advanced materials for reactor pressure vessels to withstand higher temperatures. The National Nuclear Laboratory in the UK is testing improved fuel rod cladding materials for longer lifespans. Journals such as Nature Energy have published papers modeling load-following capability, which is the ability of SMRs to adjust output to match grid fluctuations. This flexibility could help balance variable wind and solar, something that large conventional reactors struggle with. Another area of investigation is the integration of SMRs with district heating and industrial applications. Because the reactors produce high-temperature steam, they can be used for hydrogen production through electrolysis or for providing heat to chemical plants. Rolls Royce has discussed potential industrial customers in northern England, where chemical and steel industries are concentrated. Using nuclear heat directly for industrial processes reduces electricity demand and enhances overall energy efficiency. This side application could become an important revenue stream beyond electricity sales. International competitors are also advancing SMR designs. In the United States, NuScale Power has received design approval from the Nuclear Regulatory Commission and plans to build the first module in Idaho. In Russia, Rosatom has already deployed floating SMRs on barges to provide power to remote regions. In China, the HTRPM project, a high-temperature gas-cooled modular reactor, achieved first criticality in 2021. Each design has unique features, but Rolls-Royce emphasizes simplicity and reliance on proven pressurized water technology. This lowers technical risk compared to more novel designs. By 2026, Rolls-Royce expects to complete the design approval process and begin preparing manufacturing facilities. The company has identified sites in northern England for production lines capable of producing multiple reactor modules per year. Once operational, these factories could support both domestic and export markets. The goal is to establish the UK as a global hub for SMR technology, similar to how Airbus established Europe's position in aviation manufacturing. Government support is crucial in this phase, and funding decisions in Parliament will influence whether full-scale deployment begins later in the decade. One additional consideration is waste management. Although SMRs produce less total waste than large reactors, the waste is still high level and must be securely stored. The UK is developing a geological disposal facility program to handle long-term storage of spent fuel and high-level waste. Rolls Royce SMRs will rely on the same program, which is currently in the site selection stage. The National Nuclear Laboratory has emphasized that integrating SMR waste streams into a unified national system will be necessary for long-term safety and regulatory approval. Another future application involves coupling SMRs with renewable microgrids. Because of their smaller size and modular output, SMRs could provide stability to isolated renewable heavy systems in regions like Scotland's Highlands or remote islands. Studies by the University of Strathclyde show that SMRs integrated with wind and tidal energy reduce curtailment and improve grid stability. Demonstrating this hybrid model could support export opportunities, as countries with high renewable penetration often face similar stability issues. Looking further ahead, SMRs may evolve into advanced reactors with higher efficiency. Researchers at ETH Zurich and the Max Planck Institute are studying how modular reactors could eventually integrate with molten salt cooling or fast neutron designs. These could improve fuel utilization and reduce waste. While these are longer-term prospects beyond 2029, the initial generation of Rolls Royce SMRs provides a practical foundation for Britain's energy transition. Demonstrating reliable operation of the first units will be the critical milestone. In summary, the Rolls Royce SMR represents a shift in how nuclear power can be built and deployed. It uses established pressurized water technology, but applies modular construction methods to reduce costs and timelines. Passive safety systems increase resilience, while scalability allows gradual growth. The UK is positioning itself as a leader in this technology, with international interest already evident. If challenges in financing, regulation and supply chains can be overcome, the SMR could provide reliable low-carbon power well into the mid-21st century. Thank you very much for watching. Please like and subscribe.